Traído a ti por la química.
Brought to you by chemistry.
Hi everyone, and welcome to Brought to you by Chemistry. What's brought to you by chemistry, I hear you ask? Complicated reactions? Complicated exams? Even more complicated romances? You know, the ones that most people wouldn't understand, but it's okay because you have blind faith that it will work this time. I mean, yes, but in this case, Brought to you by Chemistry is a podcast series from the Royal Society of Chemistry, so you see the branding there. My name is Dr. Alex Lathbridge, and in this series we are back and better than ever because we're taking a look at batteries, bringing together experts from inside and outside the world of chemistry to help us understand the ins, the outs, the ups, the downs, the positives and the negatives of all things battery. Could I please get you to introduce yourself? I'm going to go with Serena. Could I please get you to introduce yourself?
Hello, my name is Professor Serena Cussen. I am the Head of Department of Materials Science and Engineering at the University of Sheffield, where I run a research team dedicated to investigating next generation of energy storage materials specifically for batteries. So it's really great to be with you today.
Wonderful. I'm glad to have you here. And of course, second wonderful guest, please introduce yourself.
Yes, my name is Robert Llewellyn, and I'm just coming up to the 50th anniversary of my expulsion from grammar school, which gives a slight distinction in the educational process that I went through from Serena's. I'm not a professor. But I was quite a clever kid. I'm going to defend myself, but very, very annoying, which is why I don't blame the school for expelling me. I deserved it. But so for the last 12 years, I've been making a YouTube series called The Fully Charged Show about electric vehicles, battery technology, renewable energy, the energy transition we're going through. And for the previous 25 years to that, I was involved in various types of broadcast television, most specifically relevant to what we're talking about today, a show called Scrap Heap Challenge, only because many engineers now who I've met watched it when they were young, which was an engineering challenge show. Let's leave it there. And I've done some science fiction nonsense as well.
Wonderful. Now that we've got, the basic stuff out of the way, both of you are going to lead me into the world of things that I know very little about, which is batteries. And, people are listening to this podcast because they want to know about batteries. We're going to learn all about batteries. And of course, my very first question I'm going to say, Professor Serena Cussen, what is a battery?
It's a great question. A battery is typically made up of a positive cathode, you have a negative anode, and then between those two, you have an electrolyte. And when that cathode and anode are hooked up to an external circuit, that permits the flow of electrons. So what you have happening in your battery are a series of chemical reactions, and they cause a buildup of electrons at that negative anode. Now, the electrolyte stops those electrons from simply just moving across the battery to the cathode side. And that means that those electrons can instead move through an external wire connecting the anode to the cathode, and along the way they can perform their function. So on top of that, there's other stuff happening too. So in a lithium-ion battery, for example, we would have the movement of lithium ions as well as electrons. So you'll have heard processes like your battery is charging or discharging. Let's think about what that means.
Yes, please, definitely, because we've jumped into anodes and cathodes and electrolytes. Electrolytes are what is in, sports drinks and whatnot, right? So
well, it's salts, yeah. So it's similar in a battery. So okay. It allows that movement of those lithium ions, those charged particles, through that electrolyte. So if we think about charge, you've got your positive electrode or your cathode, and what it does is it gives up some of its lithium ions, and those lithium ions then can move through the electrolyte to your negative anode. So for example, in current lithium ion batteries, that anode could be graphite, and during that process, that's when the battery is taking in and storing energy. So then when your battery is discharging, the lithium ions are moving back through the electrolyte into the cathode. And that is the energy then that's powering our battery. So in both cases where you have, you charge and discharge, you've got electrons flowing in the opposite direction to ions around that external circuit. So if the ions, like your lithium ions, stop moving through that electrolyte because, for example, your battery is completely discharged, then electrons can no longer move through that outer circuit, so you lose your power. So that effectively is how your battery will work.
I know that I should know those words and that I should understand most of those words. I'm going to say that I do, right? I do get it. And I sort of understand it, but I'm going to jump to Robert right now. I mean, for someone like you who's done all of these things, you know, tinkering, making, understanding, enjoying engineering and whatnot, getting expelled from school when you were younger, why do you care so much about batteries? I mean, you agreed to come on a podcast about batteries.
I mean, I think what we're seeing now, and this certainly emerged about 15 years ago with the sort of first generation of electric vehicles that use lithium-ion rechargeable batteries. You know, and the very early versions of those vehicles were, you know, extremely rare and not terribly efficient, and they were very expensive, and they didn't work very well, and there was, you know, all those things were there. But there was an emergence, and what I think is interesting, particularly in this case, is that transformation came out of the computer industry, not the automotive industry. The automotive industry, until really, I would say 2 or 3 years ago, was 100% locked in, granite jaw, determined to keep on with combustion engines, no matter what anyone said or what any government said. And I think finally that granite jaw has got a crack in it, and they're starting to change their mind. But that aside, the emergence of rechargeable lithium-ion batteries was adopted by the computer industry and the small gadget industry, cameras, recorders, cell phones, laptops, all those things. That's where it was initially adopted. And I mean, I think the history of that is quite fascinating.
Mm-hmm.
And I mean, I know Serena will know this, but it was about the time I was expelled from school. You had a very clever man called Professor John Goodenough in Oxford, which is where I lived. I didn't know him, and I'm sure he wouldn't have encouraged me to carry on being expelled from school. But he developed that. That's his team at Oxford University developed the first lithium-ion rechargeable batteries, which nobody wanted, no one was interested in, except about I think it was in the early 1980s actually. Some people from Sony, the Sony Corporation in Japan, came over and said, you know, those batteries that no one's interested in, can we have some? And the rest is kind of history. So I think that's where it is. And the knock-on effect that I definitely didn't see, for instance, at the moment, I'm in my house, everything is running off batteries and solar panels. I haven't used mains electricity now for 4 days. Not one electron has come from the mains system because it's been sunny. Not like that all year round.
What a flex. That is the nichest flex. The listeners of this podcast will appreciate that, because that's a very niche. No single electron has come from outside my closed circuit. I am the 21st century off-grid man. All right.
But I'm definitely not off-grid because I like being on the grid. I'm a very keen proponent of the grid. It's very important.
I'm pro-grid.
Please don't say I'm anti-grid. I'm very pro-grid. Because I also sell electricity back into the grid, but I've been using it all here recently, but yes. But then, and also just to really highlight that, I can't do this in the winter when it's not sunny, you know. So we've been getting a lot of solar recently, so that's really helped.
I mean, you know, that journey that you've come on from being suspended at school, which I feel is a really good jumping off point. I really think that everyone should have been. I think
no, they shouldn't.
Hang on, I should step in here.
You should, Serena. You did a proper education.
No, Serena, I feel as though at this point you'd be an emeritus professor, which I assume is the super professor. I don't know. I just learned words off Wikipedia. If you'd been expelled. But, you know, based on what Robert's saying, and I guess for you more in general, like, how important are batteries for like a sustainable future? How can I get to the point where Robert is, where for the last 4 days, like, I haven't used mains electricity? How can I be like that?
I mean, I think they're vitally important. We are in the midst of a climate emergency, and I think staying the current course would be catastrophic. I think batteries are one of those energy storage technologies that could really enable a greener grid. it's a hugely exciting time as we move towards a more electrified future, because the reality is that we are seeing effects and very real evidence of climate change. And I think unlocking the potential that battery technologies will have real impact in that particular example that Robert's talked about, where you're thinking about that transition from fossil fuels to renewable energy sources. So, you've got energy storage technologies like batteries, which could play a key role in that decarbonising of our energy system. If you imagine what Robert was talking about, that the energy grid as being that careful balance of matching supply with demand, you can definitely see the role that batteries have to play there. Because when you add renewable energy production into our energy system, we really start to face that challenge that Robert mentioned about wintertime. But the wind doesn't always blow. Unfortunately, in the UK, the sun does not always shine. So there's going to be those inherent peaks and troughs in our energy supply, in our renewable supply. Now, but in 2020, our renewable energy generation in the UK actually met over 40% of our electricity demand. So there is a really clear need for storing that energy and making sure that we have that necessary flexibility to be able to deliver that energy where and when it's needed. So I think that batteries have a huge sort of opportunity here. There's lots of chemistries under that umbrella of batteries that could potentially play a role. And I think that one of the areas that I'm speaking now is as a materials scientist, but I really think that in terms of delivering a more sustainable future that you mentioned, that material science and chemistry has an enormous role to play here. I think if you look at a battery, we mentioned earlier about battery has, the negative end, positive end, you've got this electrolyte in the middle, then you've got the packaging it's within. Robert talked about the production of these things and how you package them together. Any kind of technology like that sits at an interface of multiple research areas. And so you really need a commitment to collaboratively working across those areas. And by doing that, I think you can, and I think we are seeing more sustainable ways of making materials. We're making use of more earth abundant elements in our energy storage materials. And I think we're starting to think more deeply about the environmental impact that those materials might have. And I think as a researcher working in this field, I think it's extremely important challenge for all researchers working on energy storage to make sure that we think about any new materials that power our batteries. We take into consideration those wider economic and social science implications of any technology development. We have to make sure that everything that we do is sustainable. And I think that means you can recognize then even the wider benefits of what you do, that any movement to a more sustainable future promotes human welfare and it advances our society as a whole. And I think all of those activities can further contribute to decarbonisation efforts and that role that batteries will play in that.
So, with that in mind, first from your perspective and then Serena's, are certain types of batteries better or worse for the environment, would you say?
Oh, I'm sure. I think anything that human beings make, particularly if they dig stuff up to make it, has an impact. And you could argue that any of it is bad for society. And the one thing we've been doing for the last, say, 125 years is extract oil and burn it. And I think we now understand that out of all the extraction industries, that's really quite a negative thing to do, because however hard we've tried, it's really difficult to burn something twice. It's very easy to burn it once. But, I've always asked people who are very pro fossil fuels and combustion engines, I say, show me a litre of recycled diesel and I'll buy a diesel car, if we could use that again. And I think that's the critical difference. And we have to make sure that is built in, which is very much as Serena was saying, that is built in from the get-go, if you like, although I hate that phrase, but that we design the battery chemistry and the materials that we use in it to make it as easy as possible to then at the end of life, which I'm going to argue is 15 to 20 years, not 5 minutes, at the end of life, we can use those materials again. And I think a critical point I always want to make is that the one of the key people behind the emergence of the Tesla Motors company was a guy called JB Straubel, who I've met once, who's an extraordinary quiet man. He doesn't get in the news a lot. And he left Tesla a few years ago. He was absolutely instrumental in the development of their software, their battery systems, their drivetrains, which are still, annoyingly, because I'm not a Tesla fanboy, even though I drive them, annoyingly, they're 10 years ahead of anyone else. And it is annoying. And other people really need to catch up. But he left and he started a battery recycling company called Redwood Materials in I think it's in Utah, in America. And at the moment, there aren't car batteries to recycle because they're lasting too long. But he's recycling billions of tons of old phones and laptops, which we've all thrown away without a second thought. And it's so critically important. He's extracting materials from those batteries and selling that material to Tesla, who make batteries from it. You cannot do that with fossil fuels. You can do it with an engine. A combustion engine, you can melt it down and reuse that metal, but you can't do it with the fuel. And I think that's the critical difference. So yes, definitely there are, and I wouldn't want to name them. I think Serena will know, the good, the better and the worst environmental damaging, and not only environmentally damaging, ethically damaging, where the materials come from, who extracts them, are they paid, how is the environment affected by that? All those things are really vitally important, but they're also changeable, and often the general press is 5 to 10 years out of date in their biases and bigotries, which can be frustrating that things have changed. And also, I think one of the few things that I feel confident does is one of the new battery technologies. And again, this would be, Serena would know way more about it, but I've heard of so many different types of battery forms that are emerging, and I think 99% of them are they're going to fail. They're not going to work. But one of them, you're going to go in 10 years' time. We can't tell now. In 10 years' time, they'll go, oh, was that? God, I heard about that in 2007. I never knew that would actually happen. One of them is going to work. And it's not impossible that we could have a transformative, higher density, lower weight, smaller, longer lasting battery, which doesn't have a lot of those contentious materials. And currently, we cannot do anything with combustion engines. We've taken them to the absolute limit of their reliability, their efficiency. There's nowhere else for them to go. 150 years of development. There's an enormous distance that we can still go with battery technology and the materials that's in it. I'll shut up.
I love the energy more than anything. So, Professor Serena Cussen, could you tell us? What's your perspective on this from the chemistry, the materials, the research perspective? Are some batteries better or worse for the environment? I really hope it's not AA batteries. They're my favorite.
I think it's a great question. It's very broad, but really, really important. And if it's okay with you, I'll sort of think about this from safety, recycling, and ethical concerns are quite similar to what Robert was saying. You will have heard about safety issues around some batteries that have led in the past to things like product recalls of consumer goods. And I think that really serves to highlight the need for us to really deeply consider our research into the safety of batteries. So, for example, Robert mentioned there's lots of potential battery chemistries out there. One of them is the solid state battery. So at the moment, we cannot safely use lithium metal as an anode in a liquid electrolyte battery. Now, why does that matter? Well, it would be great to be able to do that because lithium's really light. So that would give us a lighter battery and it would be higher energy density. So that's great for your battery car range. But we face huge safety issues there because the buildup of lithium can cause the growth of something called lithium dendrites. These are like little whiskers. I don't know why I'm pointing at my face, but little whiskers of lithium.
This is an audio medium. This isn't video. So
it helped me. It helped me understand what whiskers are.
Yeah. So for people listening, imagine sort of a Hercule Poirot. If anyone used to watch ITV2, it's she's doing the little mustachy whiskers like a cat to explain this. So please explain this feline concept.
So you could imagine these sort of whisker-like buildups of lithium that can protrude through your battery cell. And what happens there is it can cause huge safety risks and the potential for fires. So there's a huge amount of ongoing research in that area of looking at safer alternatives. looking at things like ceramics, which can replace those flammable liquid electrolytes, but still allow the movement of ions through those solids. So that's really quite exciting. Another area that, in terms of, are some better than others in terms of being better or worse for the environment, you've got to think about how you're actually going to transport these things as well. So we do face concerns when we think about transporting lithium-ion batteries, because they can't be fully discharged, and that can lead to considerable transport costs. So in that case, we've got the advent of things like sodium-ion batteries, which are really very exciting because sodium-ion batteries can be fully discharged, and that avoids a danger of thermal runaway, which can be caused if you short circuit. And so that makes transport much, much more efficient. So there's that aspect as well of environmental concern. Robert's already touched on the recycling piece, which I completely agree with him. I think in terms of the environmental impact of end-of-life batteries, we have this huge predicted growth of electric vehicles in the UK, and that represents a really significant challenge around waste management. And I think there's vital work to be done on recycling and reuse of batteries. And there are teams in the UK working to establish not just the technological framework, but also the legal and economic infrastructure that you need to have around that battery materials recycling piece. And I think there's huge value in developing those kinds of methods where you harvest critical elements that are not earth abundant. So you might reuse them and reapply them. When you think about that, a question of earth abundance, there's 3 countries in the world account for 85% of global lithium production. And when you go to mine things like lithium, it's often done through brine extraction, and that's really water intensive. And existing methods typically rely on solar evaporation from these really large salt flats to crystallize out other salts. And that process can take months or even years. So there's opportunities there for new filtration techniques that are at quite early stages now, but that could reduce those processing times. And I think we need to be implementing those kinds of recycling strategies. And as Robert said, consider second life scenarios for batteries that have already delivered on their primary function. And then going back to that awareness of ethical concerns around child labor, around the mining of elements like cobalt in batteries that's used very widely, as well as building more responsible cobalt supply chains. I think this is another place where material science and engineering can play a huge role in terms of designing new materials that limit our reliance on those kinds of elements so that we can apply more sustainable earth abundant alternatives.
So let me flip it. And because you gave a most wonderful answer, I'm going to start with you, but Robert will probably have some opinions on this. I think everyone will have an opinion on this. What do you think, like right now, what would a world without batteries look like?
Oh, wow. Okay, that's a really interesting question.
Because there might not be, Robert, I hear you have a YouTube series called Fully Charged. What happens if there's nothing to charge? I mean, Serena,
okay.
What would happen in a world without batteries?
I think it's a great question. And I suppose I go back historically and think, it's amazing to think that over 100 years ago, you had people like Tesla, people like Edison, engaged in this huge contest, right? This fierce competition about distributed electricity grids and transmitting electricity over these really long distances. Could you imagine how they would find looking at today and how fascinating it would be to see that technology evolved beyond grid-based systems? So things like batteries have revolutionized the portable electronics industry. You see huge benefits for off-grid communities that can now access crucial services like finance, like health, like the internet. And I think very often, if we look back to the discovery of things like lead acid batteries by Plante, that was the mid-19th century. You started to see batteries penetrate into transport and starting to power the lights and train carriages. And now today you see that electric vehicle revolution. So I think I would struggle to imagine what a world like without batteries would look like. And I think we have this huge opportunity where, you think about the pioneering work of Nobel Prize winners like John Goodenough, like Stan Whittingham, like Yoshino, who have revolutionized that portable industry just in my lifetime, and how batteries are now contributing to electric vehicles. That huge critical role they're going to play in that movement away from fossil fuels is just really exciting.
It feels you've taken what is a not negative question, a quite difficult and maybe sad question, and turned it into a huge positive, which I like. And speaking of turning negatives into positives, batteries. Robert, what do you think a world without batteries would look like?
Oh, and it is hard to imagine because they have been around as long as combustion engines, effectively, in one form or another. I mean, I think there was a very early battery on display at the Royal Institution, isn't there? Was it the Volta? It was basically
the Voltic pile, yeah.
The Voltic pile. It's a load of bits of leather and zinc, and so that was. I don't know when that was. That was a long time ago, a couple of 100 years ago. So it's hard to envisage it, but I mean, I think in fact, Nissan did an advert for the Nissan Leaf when it first came out, where everything was powered by combustion engines. And so there was someone in a cafe and they wanted to pay their bill. So the person got the card reader, but they had to start it, and it has a little and a bit of smoke coming out. And then there was a woman with a food mixer, and that had a petrol engine driving it. So it was joke. And I think there was a dispensing machine, putting $1 in and getting a can of Coke out. One of those vending machine. There was a vending machine that had to start its engine to vend anything. So they were sort of describing a world without electricity, effectively, only combustion. But so I can't quite picture it. It's like, if we had never developed combustion engines and we'd never extracted oil and burnt it, the world would be very different. It might be worse, or it might be better. I mean, it's very hard to really imagine a world without batteries. We certainly couldn't do a lot of the things we take for granted now. I mean, my laptop is running on a battery at the moment. So, they're just a ubiquitous part of our, aren't they? They're part of our lives, and we don't even notice. Even these little things, that's what I think is more freakish, because I grew up with wire. Everything had to have a wire when I was a lad. And I've got two little things in my ears that I think have got batteries in, because they work and they're electronic. I don't even know. The batteries have got to be pretty small. So it is hard to envisage that.
So, I mean, you've both talked there about, taking the past until to now. I mean, in terms of like what's happening now towards the future, Professor Serena Cussen, can you please give us like an overview of your research into batteries? I mean, what's on the horizon? What's coming next? What's the next thing that Robert can talk about on his YouTube channel, which is fully charged if you want to subscribe on YouTube?
Well, I think very often you'll hear battery researchers talking about things like energy density and power density of batteries. So I'm going to tell you what those things mean before I tell you what we're doing about them. So energy density tells you about how much energy your battery can store in a given mass or a given volume. And then power density is telling us about how quickly that device can then deliver that energy. So you can think about it like a race. If you were running a 100-meter race, you need to deliver that power very, very quickly to accelerate, like think Usain Bolt here. So you have very high power density. But if you want to run a marathon, you need to be able to maintain that energy over a really long time and have very high energy density. So you want to be Paula Radcliffe. So your energy density measures the ability that you have for how long you can store energy, whereas your power density is how quickly you can release it. So a lot of the research that we're doing at the moment is trying to optimize those kinds of characteristics in batteries, making sure that we can deliver batteries that have that long lifetime, that can deliver energy over a long period of time, or if you want to accelerate, that can deliver that acceleration. So we're also trying to do that in a way that, going back to an awful lot of the conversation we've had up to now, that reduces our reliance on expensive elements and moves to sort of more cheaper, more sustainable alternatives. And of course, we want to pair that with smart engineering. So we're trying to think about how we might significantly reduce the cost of our battery without limiting its lifetime or its energy density or its power density, and do it in a safe way. So in terms of what my research is doing, I have the huge privilege to lead a very large consortium of researchers through the UK's Faraday Institution. We're working on next generation cathode materials. So remember, the cathode's the positive part of the battery. And we're a project called FutureCat. And it's a UK-wide collaboration. It's fantastic to get to work with so many people across so many different scientific and engineering fields, led out of the University of Sheffield. And we're working to deliver new routes to high performance cathodes. Cathode represents the most expensive part of your battery at the moment. So there's a huge opportunity there for material science and chemistry. We're also trying to develop ways in which you could prolong the performance and the lifetime of these battery cathodes, as well as discovering brand new cathode chemistries where we apply much more earth abundant elements for more sustainable batteries.
I mean, I'm very charged up about this. I'm sorry, the battery puns. You said Usain Bolt, so I thought we were stacking up battery puns. Sorry if we're not. I mean, Serena, what is stopping us from getting further ahead? What's stopping us from having like a super powerful battery in the palm of one's hand?
There's a lot of challenges in terms of delivering a brand new battery chemistry that can make that transformative step change. I think there are candidates on the horizon. So I think that things like solid state batteries, for example, I mentioned earlier that at the moment we can't use lithium metal. If we could, that would see a significant improvement in energy densities and also in safety and sort of making smaller batteries as well. And I think that would see a significant step change. I think when we look at, you talk about the incremental changes in batteries to date. I think when we look at some of these more earth abundant alternatives, so I mentioned manganese as an example, moving from nickel to manganese. These have really, really exciting potentials. So let me explain why. At the moment, some of our battery chemistries, they rely on our metals giving up or receiving electrons during all of their work in the battery. So if we could move to a situation where it's not just our transition metals, but also other elements present in the battery are involved in those electron transfer reactions as well, it's increasing the capacity of our batteries or improving, potentially significantly improving our energy densities. So it's sort of thinking about things in a different way. Now the challenge there, of course, is we're trying to step change here in terms of performance, but it does require a huge amount of fundamental research to understand how these processes work. And if we can understand them properly, then we can take full advantage of them.
Okay, that's made me really hopeful for the future. And I think, like we've mentioned, one of the big places you're going to see batteries being used, at least as a consumer, it's going to be consumer vehicles. And when people think about that, they think about electric cars. But, Robert, I've seen on your YouTube channel, I'm not going to name it, people should know it by now, but it's fully charged if you want to subscribe. You don't just have electric cars, you have electric boats, and there's something that I've been considering getting, an electric bike. There are electric bikes. So for you, I mean, just even looking at vehicles for now, like, is there what would the perfect battery be? I mean, what would you like to see in that respect? I mean, right now you're putting it forward to Professor Serena Cussen. She might be able to make it happen. So like, yes. what would the perfect battery look like?
I think the answer is there isn't a perfect battery, because there are many roles that a battery can fulfill, and therefore you want different technologies for different roles. So for instance, one of the things that is often overlooked by people who aren't in the bubble of electric vehicles and on the technology surrounding that is that, for instance, I had the very first generation Nissan Leaf, the very first production electric car built in 2010 in Japan. And I've replaced the...
Look at the flex here. He's like, Serena, have you noticed this entire thing? We've been chatting chemistry. He's been like, oh, so I actually had I've met this person who worked at Tesla and who now recycles at one time. Oh, I had actually the first electric Leaf, Nissan Leaf when it first came out.
What kind of first? It was one of the first.
What kind of electric battery hipster are you? But yes.
Oh, well, I did travel to this interview on an electric bike. So,
there you go.
There's my bit.
Way ahead. Way ahead.
Okay. Sorry, Robert. Continue.
But sorry, no, what I was going to say is I've replaced the battery in that car recently, which is not going to happen in all cars. This was a very, very early stage electric vehicle. It had multiple drawbacks. I mean, I usually use slightly worse language, but when it was brand new, the range wasn't impressive. And after 10 years of use, the range was slightly less impressive. So it was never particularly amazing, but it's now had a much bigger battery put in, and that is a clue. So it's had a much bigger capacity battery put in, same weight, same size, fitted in exactly the same slot. Took about 20 minutes to swap it. Very, very quick process. A lot of software problems. So now, because the software was fairly crude when it was made, so now when you charge it up overnight and you look at it in the morning, it says 168 miles range, and you literally drive 10 meters and it says 110 miles range. So it's adjusting in a very violent and aggressive way. But that said, the battery that was taken out is now running a small workshop and office. It's been repackaged into a little box. It's got a control system on top, very simple bit of electronics and software that runs it. And it operates as the batteries do in my house. And that, I've been to an apartment building in Paris that has about 40 Renault Zoe batteries, old Renault Zoe batteries that basically back up the electricity in that building. So it's multiple apartments, lifts, garages with electric car chargers, and they can maintain their electricity flow at the minimum cost for the recipients. And more impressive than that is Antwerp Football Stadium, that is powered partially by huge amount of solar panels on the roofs of the auditorium. Well, I never know what to call a football pitch. What's the thing that surrounds it? The stands. Sorry, on the roof of the stands, loads of solar panels, and I think it's literally hundreds of Nissan Leaf batteries repackaged, and that runs hugely off its own power source. It's kind of a mini power station. So the second life of those batteries is, which Serena did mention, is much longer than we thought. Because if you make a battery and you put it in a car, you then accelerate that car as hard as you can, which people who drive electric cars want to do occasionally. The strain you're putting on those batteries is phenomenal. You then put that battery in a house and you turn on your cooker. That's like you almost reversing at less than walking speed. That's the demand it's putting on that battery. It's a tiny proportion. Therefore, those batteries last for years and years in their second life role. The range of the car was reduced, but the actual capacity of the battery that came out of my Nissan Leaf is about 18 kilowatt hours. Well, that'll run a house for pretty much a day. That's a really good, it's not pointless. It's not worthless. It's worth a lot. So there's that side of it. I think the other critical thing I wanted to say is that if you are going to build a massive battery that backs up the grid, I think at the moment that is being done. For instance, Tesla's big battery in South Australia is a lithium-ion batteries in big boxes. I mean, it's megawatt hours it can store. There's hundreds of them. And it might be possible that there's more suitable technology and battery chemistry to do that sort of heavy. It doesn't need to be transportable. It can weigh hundreds of tons. It doesn't matter because it's not going anywhere. So there's different types of batteries for different types of solution. That's the thing. And the other one that I've seen in Australia as well is, I think, vanadium flow. I might have got the name wrong, but flow batteries. So all the cell towers, the remote cell towers in Australia that distribute the mobile phone signal have a small solar panel, not much, and a little flow battery in a box at the base of them. And that gives them 24-hour secure power so they can run without having to be connected to the grid, because some of these are really isolated. They used to have diesel generators. Those needed constant maintenance. They've got rid of all those. They then had lithium-ion batteries, which they found were struggling with the heat. And vanadium flow batteries, the ones that I saw made by a company called Red Flow in Brisbane, they actually benefit. They get better if they're drained to 0%, and if they're charged to 0%, they prefer, which a lithium-ion battery, you want to protect it from doing that. So it really suits the environment it's in. It doesn't mind about hot and cold. It's not bothered about those things. It doesn't get affected by that. It lasts for decades. We don't even know how long they'll last. It lasts a hell of a long time. And it would be utterly unsuitable for a vehicle or a ship, or a car. Completely useless there, but brilliant for that sort of grid backup. And lastly, the one thing I want to say is batteries have got hugely better since I had bought my Nissan Leaf as an early adopter in 2011, because the capacity and the energy density has improved enormously. And up until very recently, the cost has dropped precipitously. Now that is being affected by, as we were hearing, commodity prices now. So there may be a bit of a kick up in the other direction, but I think long term, they're going to get cheaper. They're going to last longer. And the last thing I really want to say is it's very important to remember, because cobalt, very, very contentious material. Cobalt has been used for the last 50 years to refine oil. And no one talks about that. And large amounts of cobalt are needed for us to remove sulfur from diesel and petrol. And it's not recycled, that cobalt. So I just think it's always worth mentioning, because the cobalt was used as a stick by the fossil fuel industry to beat the development of battery technology. And all the time they kept very quiet about their large usage of cobalt, which is, I think, a good example that there are some people who lobby for some companies that are less than scrupulous or honest.
Do you mind if I pop in on that? I think when you're thinking about a technology for a particular application, I think it's really crucial that you think about what you want, but what you can have. So you might like to have very large storage capacity at low cost. You'd like to be able to deploy it very widely. You'd like to be able to have some flexibility in how you deliver that would cover sort of minutes to months. And so I think if you're going to think about how batteries sit within that space, you could see that, for example, something like a lithium-ion battery would be in a prime position to deliver at timescales up to a day, like you were talking about.
Yeah.
Whereas things like flow batteries are much more suitable for several days. So it's thinking about which chemistry is right for the application that you want to use it for. And then just thinking about your point about second life, I think there's a big piece here about understanding second life and what's possible in that second life. And we see there's a really huge number of challenges that scientists and engineers are facing at the moment around maximizing the lifetime of current lithium-ion batteries. So if you take into account, for example, a current lithium-ion battery technology, we call it NMC. So the N stands for nickel, the M stands for manganese, and the C stands for cobalt. That cathode material, you can think of it like layers, like sheets of paper. And when we're charging a battery that has that kind of cathode, remember your lithium ions are moving through the electrolyte into those layers back and forth as you charge and discharge. So the lithium ions move back through the electrolyte during that discharge into that positive cathode,
So
happening hundreds of times.
Just checking. So they're going like up and down through these layers. So
if you think,
like a lasagna. Like a
lasagna sheet, exactly. So
okay.
think of a lasagna sheet, and that those lithium ions moving in between those sheets of pasta and back again. And if you imagine that happening hundreds of times, and those layers could be, you could think of them like sheets of paper or like sheets of pasta. They'll start to degrade over time. Like Robert was saying, if you're really driving that car, really accelerating, really pushing it to its limits, you could even imagine those sheets starting to collapse a little bit. And that, of course, has significant effects on the capacity of your battery with time. And so lots of people, especially here in the UK, are looking at how to mitigate those kinds of degradation processes. And again, if we can understand how those layers degrade or how battery capacity fades over time, that's where we start that pathway towards designing better batteries for the future.
So when I think about like batteries of the future, which is very far in the future, English, strange language. Like I don't think about just electric cars, electric bikes. I think about like planes, like electric planes. Robert, I mean, you've been flexing on us this entire conversation, from everything to going to Australia to being kicked out of school so you could live your life fun and early. Like electric planes, do you reckon that they're going to be a thing.
I'm very ashamed because I talked about my Nissan Leaf, and I was rightly teased about that and about my all the other things. A couple of weeks ago, I flew in an electric plane for the first time. So I didn't want to say that. I didn't want to say that. This was a long time ago, before he was a well-known international figure. An actress that I very, very knew from a distance. I didn't know her at all, but she came up to me at a party, and she's that doesn't happen to me often. An attractive young woman came up to me and said, "Oh, hello, Robert, it's lovely to see you." Da da da. And then she said, "Oh, come and meet my husband." And I'm going to admit there was a slight disappointment in me, that she was going to introduce me to her husband. Her husband was a man called Elon Musk. And I went up to this man and I shook his hand. And this is our entire conversation. "Nice to meet you. Nice to meet you too." That's it. That was the full length of our conversation. But he was very busy. There was a lot of people there. So I did fly an electric plane the week before last. It was very windy. It was a very small plane. It's a Pipistrel, 2-seater, kind of a training plane. Mass-produced. It's not a one-off prototype. It's made in Slovakia. Lightweight 2-seater electric aircraft with a 24 kilowatt-hour battery. Can fly for about an hour very safely with a big margin for emergencies. Incredibly reliable, incredibly mechanically simple in comparison with a combustion engined aircraft. And that's a thing I suppose general people outside of aviation have no idea about. And I certainly wouldn't have done without having it explained to me in depth. But you take an engine that is essentially the same as in a car, and you take it up to 10,000 or 15,000 feet, it won't work because there's no oxygen for it to burn in its carburetors. So it has to have incredible, extra heavy, complex technology that forces air into the combustion chambers in order for it to actually operate. So a car engine would only probably work safely up to about 10,000 feet. Anything above that, and you're really in trouble with it. So you have to do a lot of work to make a combustion engine operate at those temperatures. You can take an electric motor into outer space. It would still work. It can be in a vacuum. It doesn't matter. Not that I would suggest this Pipistrel can go as high as that. But last week we went to see a vertical takeoff and landing electric aircraft that's going into production now. In the next 5 years, I think you will be able to fly regularly between sort of 100 and 250 miles in purely electric aircraft. And it may take a bit longer to do, say, London to Paris, but certainly city centres to airports is where a lot of focus is going, because I didn't even know, but that's a big previously. See, I'm doubting a lot of the sociological aspects of this. That in the past, a lot of business people needed to get from the business hub to the airport in the minimum time possible because they're so important. And actually now, fewer people are flying with business anyway. And also the whole flying thing is questionable. And also nobody works in offices anymore. So I think there's some arguments around there. But certainly there are technologies developing. Well, and I think autonomous as well, very critically important, fully autonomous short-haul flights. You two will definitely live long enough to see that as a regular, normal thing. It won't even be unusual. You won't even comment on it. You just get in a little thing and it'll fly you somewhere. Not that far, not that fast, not that high, but it will do it, certainly. So it's definitely happening. And that is 100% down to battery technology and improved battery technology. So Vertical Aerospace, who we want to see, have developed their own battery technology in-house. I don't know what it is. It's secret. They're not telling anyone what it is. But they're predicting that within, the next 5 years, they'll be achieving 250 miles. There's also Electroflight. No, there's so many different companies that are doing it. I'm trying to remember the other one. There's another company whose name will come back to me in a moment, who are doing hydrogen fuel cells and batteries for longer haul flights. And they're experimenting with that just down the road from me. It's so annoying when I can't remember the name of the company, but I will in a moment.
Yeah, when they're just down the road from you don't remember. Down the road, I remember. I have a Nando's. And I do quite like the idea that you're like, oh yeah, for the two of you, these sorts of things, flying in these battery-powered vertical takeoff and landing things, it's going to be completely normal. Bro, I'm broke. Nothing is going to be normal for me like that. So, Serena, the stuff that Robert's so enthusiastically talking about, do you reckon that timescale sort of, are you hopeful?
I think that there are certainly opportunities in the broader opportunities in transport for batteries to penetrate into, certainly. If we look at, again, you're thinking about advancements in chemistry and material science and engineering to look at things like lightweight batteries. So things that are made up of elements like lithium and sulfur have great potential for applications in aerospace. Lithium sulfur batteries in particular sort of present real opportunities in terms of high energy densities, lighter weight, lower cost batteries, which could potentially be very interesting for aviation. LG Chem batteries power some unmanned aircraft that have been developed by the Korean Aerospace Research Institute. And there are adoption of lighter weight batteries in larger electric vehicles, such as buses and trucks. I'm with you, Alex, about, that if we can make this something that's affordable, and looking to public transport opportunities where we can electrify all of that, that's a huge opportunity. But I think, again, we've got to think about how we solve some fundamental questions around the chemistry of some of these batteries to be able to unlock that sort of potential market penetration for aviation or sort of larger vehicles.
Love it. I love the optimism. I love it. So, I mean, I love everything about this. I'm in love, really, with batteries, and this is going to continue through the rest of the series, I guarantee. So my final question, always the most difficult. So I'm going to start with Robert. Very briefly, if you could have a listener take one thing away from this conversation, what would it be?
Batteries in our lives will become normal and uninteresting, which in a way is the best possible result. At the moment they're esoteric. So, the fact that I have neighbors that literally come to my house to look at a box on the wall is weird. And it's a battery, and it doesn't do anything. It hasn't got pistons or shiny bits of brass that do interesting things, doesn't make any noise. It's just completely silent box on the wall of a house. But they come and see it because they're intrigued by what it represents. And I think that's once that stops being weird, in a sense, like electric cars are becoming, there's I was in quite a bad mood the other day because for a long time I was special in my village. 28 houses in my village. I had an electric car. No one else did. I was special. I stood out. I was an elitist living in a bubble of elitist something or other. I can't remember what I'm accused of on Twitter. And now I'm common. I'm one of the commoners. There's now something like 19 electric cars in our village, which is insane how quickly that's happened. The increase in, and then there's a guy on the corner, I'm not going to mention his name, who's very wealthy, who lives in a lovely old farmhouse, and he's got a Porsche Taycan, which cost 3 times more than our house when we bought our house. So,
like this summary is just turning into a flex. Look at this posh little village I live in. Oh, I used to be special. Then everyone else got money.
Everyone else has joined in, but also I've lowered the average property prices in our village by the state of our house and garden. So, I'm proud of that.
I'm going to go to Serena. What would be your one takeaway from, or what would you want people to take away from this episode?
I think, we talked a lot about sustainability earlier. And so I would love people to take away the fact that we are, as scientists and engineers, committed to making sure that the new chemistries and materials that are emerging from our laboratories and that we're working with our industry partners with, we are taking that sustainability challenge really, really seriously. But even going further beyond that, the idea of sustainability is making sure that a future that we look to is fair and equitable. And so making sure that this adoption of electric vehicles, there has to be strategies for, how does on-street parking work? Make sure it's a coordinated effort so that there's, the right number of charge points available to everybody, all parts of our society. And I think that kind of demand and that sort of movement to an electrified future is going to take some huge joined up thinking across sectors. The scientific leadership is really important, that we are committed to more sustainable chemistries for the future. But meeting all of those targets requires leadership from all parts of our society. And I think that's a challenge that we can all embrace.
I'm not even going to say anything because that was a fantastic outro. Wonderful. Thank you both so much. That was phenomenal.
Oh, I can stop sweating.
So, of course, wonderful guest. Could you please introduce yourself?
Hello there, I'm Saiful Islam. I'm Professor of materials science in the Department of Materials at the University of Oxford.
We, of course, here on this podcast, we're interested in batteries. We love batteries. We're charged up for batteries. My puns are great, and they're going to keep getting even better. Kieran is going to edit out the terrible ones. So I guess to begin with, could you very briefly tell me why are you so interested in batteries?
Well, I suppose we all know that one of the greatest challenges in this century is low carbon, sustainable energy to help deal with the challenges of climate change and also increasingly pollution, urban pollution. So why I'm interested in batteries? Well, batteries are one of the technologies, not the only one, that can help to address low carbon energy. It's batteries are used in portable electronics, but increasingly they're being used in electric vehicles. And that's one way of reducing carbon emissions and help to deal with climate change.
All right. So I am often told about batteries. Like, people tell me that batteries are very interesting. Of course, you love batteries. Now, the battery that I always think about is my phone, right? And I'm told that it's a lithium ion battery. That's the battery that's in my phone. Can you please explain what a lithium ion battery is? Because people have said it too many times, and I'm sort of a bit scared at this point to ask.
So we know that a battery is electrochemistry in action. I view a battery a bit like a sandwich. You've got two bread slices. The two bread slices are the electrodes, and in between those two bread slices, you need a good sandwich filling. So the meat or cheese, if you're vegetarian, is the electrolyte. And in a lithium-ion battery, what's moving between the two electrodes are lithium ions. One of the electrodes is a lithium transition metal oxide, and the other electrode is graphite. So it's a lithium-ion battery because the actual ions that are moving are lithium.
You know what? When you say it like that and you sum it up like that, it feels like a silly question, but I know full well that myself and many other listeners of this podcast perhaps didn't know that. So thank you. And you've also made me think about lunch, which is another thing. I'm hungry for knowledge, but also a sandwich at this point.
Well, actually, I should add also, people might say, well, why lithium? Well, lithium is the third element in the periodic table. It's the lightest and smallest of metal ions. So we don't have, as yet, a hydrogen battery. That would be a fuel cell. We don't have a helium battery, but we do use them in balloons. But a lithium is the lightest and smallest of metal ions out there. And that's why it's got what is called a very high energy density. So you can stuff that sandwich, that electrochemical sandwich, with lots of lithium, which means it can store a lot of energy in a small mass and a small volume.
So it's like the most dense sandwich possible. It's like a ploughman's lunch.
Exactly.
Like, okay.
So that dense sandwich is that's why it can go into your portable mobile phone as a nice thin battery. And obviously we would love it to store even more, which comes onto my research, which we can talk about in a second. Well, I mean, you've teed it up very nicely. So apart from lunch and other food-based analogies, what are you working on right now? Good question.
Thank you. I thought it up myself.
We know that we charge our mobile phone every night. Supposing we could develop a battery that you only have to charge maybe once every 2 weeks. Could we increase the energy density, how much that battery can store? So one of the limitations of how much energy we can store is on the cathode side, the oxide side, which has a lower energy density than the graphite on the anode side. So my research, which is being funded by the Faraday Institution, is to develop new cathode materials that store more energy. And that's one of the big areas of research, not only in the UK, but around the world.
Okay, so I mean, you got to tell me where are you right now? Am I going to have like a micro SD card sized battery that can power my computer? Are we there yet?
Currently, our conventional cathodes are layered oxides. The prototype was lithium cobalt oxide, which led to the Nobel Prize for the founder, the pioneer, which is John Goodenough, which is long overdue, the oldest Nobel laureate at 97. And he got the Nobel Prize 3 years ago with Stan Whittingham and Yoshino. That's the conventional one. The other conventional cathodes are lithium nickel manganese cobalt oxide, called NMC. So that's currently in most electric vehicles, that NMC. What we're working on, what is called lithium-rich oxides, trying to stuff more lithium into these layered oxides, but also very new structures called disordered rock salts. We all know the rock salt structure, the stuff that we sprinkle on our
we all know that. Again, the food-based analogies. Is this what this is about?
Well, I'll bring in a drink as well. So you can sprinkle on your chips, on your rice, but in my case, I use salt just before a tequila shot. Then we could, this disordered rock salts show very high energy density as well, but they're not made of sodium and chloride. They're made of lithium, manganese, oxygen, and fluorine. So these oxyfluorides, and they're very exciting because they've got very high energy densities.
You're obviously thinking about the future. You know, you're really on it, finger on the pulse there. What role do you think that batteries could play in like a truly renewable future? Because, you know, you mentioned electric vehicles, and that's one sort of way we're going down with a sustainable future. But when it comes to like bringing renewable energies and sort of really thinking about a green future, what role do batteries play?
Yeah, that is another really good question, because as well as you say, electrification of transport and portable electronics, we've got increasing renewables. It's a really exciting time for science and engineering in general. The growth of renewables, solar, wind, there could be more tidal, but when the wind isn't blowing and the sun isn't shining, we do need energy storage. Currently, large-scale energy storage doesn't tend to be batteries, but there's no reason why large-scale energy storage could be batteries of some type. It's unlikely, although you never know, it's unlikely to be lithium-ion, because that's a bit costly. But there are big developments in sodium. So sodium-ion batteries, so sodium is below lithium in the periodic table, has very similar chemistry to lithium, but has the advantage of being much more abundant than lithium. So it would be lower cost and more sustainable. And there's thought that you could build these larger sodium-ion batteries for renewable energy, for storing energy from there. So if you haven't heard about sodium-ion batteries, you have now, but that could be another area.
I like that. I like the mic drop. If you haven't heard about it, well, you have now. All right. So my final question, of course, a doozy. In, let's say, 64 years' time, it's a very specific number, where do you think that we'll be? Where do you hope that we'll be when it comes to battery technology?
Why 64 years?
I don't know. Just picked a number. I mean, you were talking about rock salt and sandwiches and all that earlier.
Do you think 2084, like 1984?
No. I picked the number. You get to do the answer.
Okay.
Right?
Well, I won't be alive to know what the batteries will look like. I can tell you, by then, hydrogen will be an increasing energy vector. Again, for the listeners, hydrogen has the highest energy density per unit mass and volume. And there's always been talk of hydrogen fuel cells, but hydrogen has always been a problem for two main reasons. One, producing it costs energy. And if you're going to use energy to produce hydrogen, that could be carbon intensive. And the other challenge with hydrogen was storing it. How do you store it? There's always that worry of explosive tanks. But I think in 64 years' time, we'll see those two challenges being met. And we'll see more and more hydrogen fuel cell cars, but married married with new advances in battery technologies as well. So there'll be fast charging batteries, hydrogen fuel cell cars. But who knows what the cars will be like in the future? They could be levitating on superconducting magnets. There could be superconductors out there. Yeah.
I feel as though I chose 64 years time because you are ageless from your skin right now. So I assumed 64 years was the point where you'd be dead, definitely.
Well, I'm hitting a big number next year, the big 60.
Oh, what? Wow.
Yeah.
Okay. Well done. Wow. That skincare regime. Anyway, well, toodle pip. I'm going to go eat Greg's. Bye.
Lovely. Thanks a lot. Bye.
Join us next time where we'll be asking the important question, in this day and age, what actually is the point of batteries anyway? That's all for this episode of Brought to You by Chemistry. It was produced by Hiran Joshi and Elizabeth Ratcliffe and presented by me, Alex Lathbridge.